Hey physics class, back here talking about kind of the last video for our acceleration and our velocity section. Let's talk about graphical analysis of motion. Basically that just breaks down to understanding how motion is seen and used in graphs. Most of the time so far you've had only one type of graph, basically a distance and time graph, which is what we're going to show today and kind of go through review for today. So we have distance on this side, how far are you going, over how much time, and then we break it down into some different types of motion. This year eventually we'll get into the two other types of graphs that we'll most likely see, which is a velocity in time, as well as an acceleration in time graph, but that's in our linear kinematics unit, no worries here. Basically we're going to work with this one for today and understand what motion looks like on this type of graph. And we're basically, motion has to be shown in distance and in time, so that's the easiest way to work with this. We have kind of 5 or 6 different kind of motions that we can kind of have. So I have a constant motion. Basically that means you're just going at a same speed. So if I'm going at 5 meters per second, that's again a constant speed. Okay. So we have constant motion. We can be fast in constant motion. We can be slow. We have no motion. Basically you stop moving. You have backwards motion. So let's say I wanted to again head from home to school. If I started going towards school, forgot something, had to go backwards home, that backwards motion, we can show that. We have acceleration and deceleration as well. So let's go through this. Constant motion. Constant motion means that you're going to be going the exact same speed the whole time. Okay, so 5 meters per second the whole time all the way there. So when you have constant motion, you're going to be getting straight lines because we can actually, like, you have that same constant speed, so that same dots. So I'm going to show 2 basically kind of constant motion. I'm going to make one like this. So if you were to kind of actually put meters and seconds here and then kind of plot it dot-wise, it might look something like this. Okay, and then you got a nice straight line, straight-ish line, but straight line. And then you could also have this one here. Also some constant motion, but these are 2 different constant motions. So we got 2 straight lines. This one's a little curvy, I'll give it that. Maybe let's try and straighten that out a little. There we go, a little straighter. So these are 2 constant motions. Yes, absolutely, no problem. Which one's going faster though? I mean, right away you can kind of see there's a difference. They're both straight lines, so they are both still a constant motion. But one is obviously going faster. And I want us to try and describe it actually using the actual descriptors of what's on our graph, like our table here. So we have distance, we have time. So using these words, we're traveling a farther distance in the same amount of time. Like if I put an actual, if I go right here at this time and cut it, well, in this one, like let's say this is 2 seconds. The green has only gone so far in 2 seconds. This blue has gone much farther in the same 2 seconds. So they are traveling a farther distance in the same amount of time. So that's how you know that they are going fast. Basically, the steeper your slope, the faster you're going in your constant motion. All right, so there's the first 2 there. We have a no motion and a backwards. Okay, so let's kind of do a little story again. Let's say we're going to use that school one. You're heading towards school in a constant motion. So here you go. And then let's say there's a red light. So you got to stop at a red light, whether you're on your bike, you're in a car, or whatever. You got a red light, it takes a little while. Your no motion is going to be just a flat line. So we'll change it to green here for our no motion. Here's our no motion. It is straight across. Time is still going, so obviously you're still going to be moving in the time section, but you're not moving anywhere on your distance. Okay, you're in the same spot, you have no motion, so it's a flat line, so that's going to be your no motion. Let's say you are on your bike at this time. So you head into school, got your red light, and then at the red light you're like, holy crap, I forgot my phone at home. So you got to start heading back towards home. What does backwards motion look like? Well, it's going to be heading back towards the start. Your distance will be going down because you're heading back. So it's going to be heading back towards the bottom. So there's your backwards motion. Okay, and it could technically change. You could technically say you sped home real fast. And so our slope still matters. You could have it like this, as in like you are moving faster here than you are here because it's a bigger slope, but it's going back towards the beginning. That's how we know we have backwards motion, is it's going to actually head back towards the bottom of our graph here. Okay, So there's our other ones, and let's go to the last one, acceleration and deceleration. What does acceleration mean? It means you're getting faster over a certain amount of time. Okay, so your velocity is continuously changing, which means you're going to be covering more and more distance every single second. Because if your velocity is getting higher every second, that means you're covering more distance every second. So basically what's going to be happening is we're going to have some curves here. Acceleration and deceleration have curves. That's what makes them different than from the constant motion. You'll see an actual line, like not a straight line, you'll see some curves. So in acceleration, we're going to get bigger gaps in our distance as we go. So it might start off kind of slow, but as you go, you're going to get more and more distance per second. As in, like, let's say here's our first 2 seconds, and then here's our next 2, and then here's our next 2. In our first 2 seconds, we only went a little distance. That makes sense. Maybe you start off slow, and then you're gaining more and more speed, so you traveled more distance in that section. And then you're continuously gaining more and more speed, so you're traveling more distance. So there's an acceleration curve. Deceleration curve would be kind of the opposite. So let's say that you started somewhere. Again, you started at a distance. So let's say we're going to do this. We're going to do a constant motion first, because you can't just start at a distance over here. Let's say you're traveling along on a bike, you're going nice little speed, all that kind of stuff. But now you want to start slowing down. This is where the curve's going to change. So I'm going to change markers here. This is what our deceleration would look like. It would start curving until you're stopped, basically. You guys know that this, a flat, is basically stopped. That's no motion. So the deceleration curve looks like this. It's slowing down. Basically, you're traveling less distance in the same amount of time. So here, again, let's say here's our cutoff. You did still gain in distance, but you can see that now the distance is going up less and less and less, basically to where here you're stopped. There's no distance change, and that's your deceleration, basically till you're stopped. So sometime in this week when we do our little assignment, I'm going to have you do something with acceleration and deceleration. I'm going to ask you to make a graph based off of your little story. And so you're going to have to use these basically kind of these lines, these curves, to show what your actual story means. So there's some graphical analysis showing some motion. Thanks, class.